In this lecture, we're going to discuss one of the important factors in terms of performing a dynamic analysis for rotating systems, and that's the moment of inertia. And before we move on to that, this slide is a repeat of what had been discussed in an earlier lecture when we introduced this topic, dynamics, which is the branch of mechanics dealing with the accelerated motion of a body. And once again, the foundation for a dynamic analysis is Newton's second law. And we apply Newton's second law in both a linear and angular case, of course, depending upon the system that we are examining. And so key to this is to understand that mass is a measure of inertia in a linear sense, and I is the measure for inertia in the angular case. And so as all objects inherently possess a resistance to a change in its state of rest or uniform motion, we see in the linear case, mass when multiplied by acceleration will be equal to the sum of the forces that will be compelling that acceleration. And so if we have acceleration data first, we would use the analysis to estimate the forces that are compelling that mechanical behavior in a process referred to as inverse dynamics. And if we had information directly related to forces or the moments of force, and we use that to predict the kinematic behavior, that is a process referred to as forward dynamics. And so this is a repeat of a previous problem we covered, and there's a lot going on here with this slide, but please refer to the previous lecture when carrying out a dynamic analysis. And in this particular case, we're dealing with a linear situation. So we have the nature of contact between the external object and the ground, which is a surface-to-surface contact, and so we don't see any point of rotation taking place, and so we only deal with Newton's second law in the linear sense, which is the sum of the forces equals mass times acceleration. And so we typically start this approach by focusing on the forces acting in the x direction. I took a little bit of a different approach here by focusing first on the forces in the y direction, only to demonstrate the fact that the object is not accelerating in a vertical manner. So all the motion with respect to our frame of reference is happening along the x direction. And so in this problem, we had to consider the kinetic friction term, which is defined by the equation of the coefficient of kinetic friction times the normal force, or in this case we also refer to it as the ground reaction force. We had a measure for the mass of the object. We had a magnitude for the push force. This was provided to us. And so the remaining variable to be determined is the resulting acceleration the box experiences in the x direction, because going back to the original question, it asked what will happen. And so what will happen is a change in the mechanical behavior, the kinematic behavior, and that the box will experience an acceleration. Okay, but when we move to the rotational or the angular situation, the definition for inertia generally does not change. And so when we talk about inertia, it's an object's tendency to resist a change in its state of rest or uniform motion, or a change in velocity. And recall, when an object is in a state of rest, it is experiencing, it does possess a velocity. The velocity value is 0 meters per second or 0 degrees per second. And so for the object to change that state, it has to undergo an angular acceleration. So as I mentioned in the linear, when we talk about pure linear motion, the sum of the forces will equal mass times acceleration. But now moving on to angular motion, we will deal with the sum of the forces equals mass times acceleration. We'll deal with the linear case when we talk about those forces acting on the joint, but we also have to consider the moments of force. And the moment of force is equal to the moment of inertia times the angular acceleration. And so our situation will deal with planar motion, so this will be 2D motion with a fixed axis of rotation. And we'll start by examining an axis that passes through the center of mass, often referred to as an uppercase letter G. And the axis is perpendicular to the plane of motion. And the units for the moment of inertia is the kilogram meter squared. And so as we take a look at the inertial term in the linear case, the units are kilograms, but we also have to consider how the mass is distributed about the rotating system from the point of rotation. And so if we start by examining the center of mass, here we estimate a point around which the mass is evenly distributed, and the axis is coming off and into the computer screen, here. Now, when you look at this, it's natural to look at this situation and think, well, normally the leg doesn't rotate about the center of mass, it rotates about the knee joint. And what we have to use at this point is something called the parallel axis theorem. And so if we know what the moment of inertia is of an object about the center of mass, we can calculate the moment of inertia at any other point by moving the axis of rotation, provided that that axis is parallel to the axis about which the limb would rotate through its center of mass. And so in that sense, the moment of inertia of any point is going to be equal to the moment of inertia through the center of mass plus the mass of the object times the distance between the axes squared. So Ig is the moment of inertia through the center of mass, m is still the mass of the rigid body, and d is the perpendicular distance between the parallel axes. And in our knee extension example, the parallel axis we will consider here is an axis through the knee joint. And the perpendicular distance is just simply that distance between those two axes. So to explore this in a little bit more detail, a little bit more fundamentally, we see that the equation for the moment of force is equal to the moment of inertia times angular acceleration. And if we expand this into their individual units, we see that we have a Newton meter for the units for moment of force, the kilogram meter squared for the moment of inertia, and radians per second squared. So as we deal with rotating systems, we always convert our angular measures from degrees into radians. And so the moment of inertia is also defined by another formula, and that's equal to mass, m, times a new variable here that we just simply refer to as k. K is referred to as the radius of gyration. It's a little bit of a different measure, and this is a measure that measures the distance that a point mass would have the same moment of inertia as the distributed mass. So in these two examples, we'll start with the lower one here. Here we see an object where the mass is distributed in this sort of manner. Now, if we took this mass and concentrated it to a single point, as we see in this case, how far would this mass have to be from the point of rotation? And so that distance is just simply referred to as k, as a radius of gyration. And so in this case, we have this object rotating about this point, and the resistance to rotation would be the same for this object, but what we've done is we've concentrated this mass at a single, very, very small point at a particular length from the point of rotation. That's the radius of gyration, which does not coincide with the center of mass. Okay, so to examine the factors that play a very important role in an object's resistance to rotation. So here we see a system centered in the middle. We have a mass on one end, mass on the other end, each located from the point of rotation, from the axis, by 1 meter. And so there are two factors that are going to affect the moment of inertia. The first factor, of course, is the mass, and the second factor is the distance from the point of rotation, and x in this situation represents the radius of gyration. Now we have two terms in this equation because we have two masses on opposite ends of the point of rotation. If we eliminated the right mass, then we would only have one term in this equation, the m1 times x1 squared. Okay, so if we substitute the numbers for the mass of the first is 1 kilogram, mass of the second is 1 kilogram, each located 1 meter from the point of rotation, or rather from the axis of rotation, we have a moment of inertia of 2 kilogram meters squared. Now what we're going to do here is we're going to double the mass, same distance, so we haven't altered the distance. Okay, so we have this axis moving a little bit. This should not be moving, but this is a fixed axis. And so if we run through our approach once again, what's changed here is the m, mass of the first object, the mass of the second object, each located 1 meter as it was in the previous example from the axis of rotation. So by substituting the numbers here, we run through the math and we find the moment of inertia is 4 kilogram meters per squared. Functionally, what this means is that this object will present twice as much resistance to rotation as the example we worked on in slide number 7. Okay, so now one more example here. Here we see what we've done here is we've cut the mass in half from the example on slide number 8. So the same mass that we used on slide number 7, except that we've stretched the distance that mass on the left and the right is located. We've doubled the distance out to 2 meters. So we can see we're off the screen a little bit here, but we have this rotating system, and we use the same equation. The only thing that's changed is the distance from the point mass to the center of rotation. And so by substituting our values for x and for m, we find that by doubling the distance and cutting the mass in half, as we saw on slide number 8, we actually double the resistance to rotation. So the major message from these three examples is that the distance through which the point mass is located, and how the mass of a rotating system is distributed, is going to have a greater greater effect on the resistance to rotation as the mass. And so we'll work through an anatomical example here. So now what we want to do is we calculate the moment of inertia of the lower leg, and so we're going to exclude the foot, the knee, so we're just going to focus on the knee to the ankle. We have some information here. The total length is 0.4 meters from knee to ankle, and the mass is 3.6 kilograms. Now we do have to use a table. This is what's referred to as Dempster's anthropometric table. And based upon the axis of rotation, this is a key consideration in terms of reading the table. Okay, so this is a table that's been published through numerous cadaver-based studies conducted many decades ago. And so by going through those cadaver-based studies, researchers have estimated the location for the center of mass, the mass of a particular segment with respect to total body mass, as well as the radius of gyration with respect to the center of mass, or from the proximal or distal part of the joint. And so because we're going to be dealing with the lower leg here, we're going to be focusing on these numbers right here. It's also important to note that the center of mass for the lower leg is located 43.3% of the distance from the proximal end, which is the knee joint. And if you think about the mass of the gastrocnemius muscles, the muscle belly is located closer to the knee joint, then that's going to pull the center of mass of the lower leg closer to the joint. Only when you add the foot, see down here, only when you consider the foot and the lower leg does the center of mass move past the halfway point down the segment because of the relatively large mass of the foot. But for our example, we're just going to focus on the lower leg. So we're going to need this number here, 0.433, to estimate the center of mass location from the knee joint. We're going to need the 0.302 as the value for the radius of gyration about the center of mass, assuming rotation about the center of mass. And we're going to need the number 0.528 if we wish to consider rotation about the knee joint from the proximal end. Okay, so the first step here is to calculate the moment of inertia of the leg segment. Once again, we're isolating knee to ankle about the center of mass. And so we have a given mass, we have a given length, we go to Dempster's table and we pick up the radius of gyration about the center of mass because that's what we're going after here. That was stated in the question. And so when we go to our diagram, we estimate the axis of rotation going through that center and the leg rotating about that center. And so this is important to estimate because the value here will give us some indication of how much resistance an external force will face in attempting to accelerate the angular motion of the lower leg about the center of mass. Okay, so we have our formula for I center of mass for the moment of inertia. That's going to equal to the mass of the leg times the radius of gyration. But now the radius of gyration is a ratio value. It's basically 30.2%. And so what we do is we take the 0.302, we multiply it by the full length of 0.4. So from the table, these are unitless values. And when you take a unitless value, you multiply it by a length value of 0.4 meters. The final product will take on the units of meters. And so we work through the math here. We calculate the product, square it, giving us a meter squared, and so we have a moment of inertia of 0.0525 kilogram meters squared. So now you ask, well, the leg in this, at least with this type of scenario, rotates about the knee, not about the center of mass. So now we've changed the question, still the same leg segment, knee to ankle, but we're considering rotation about the knee joint. So we're moving the axis of rotation from the center of mass up to the knee joint. Now we have to select a different radius of gyration. And so based on Dempster's table, we have K proximal, since that's the proximal joint, of 0.528. And the formula hasn't changed. We use the exact same formula. And we have the same mass, 3.6 kilograms. We have the same length, 0.4 meters, but now we have a new ratio, 52.8%, or 0.528. So we substitute that value for the radius of gyration. Of course, it's going to be squared, and we work through the math, and we find a much higher value for the resistance to rotation if we're rotating about the knee joint at 0.1606. So a full order of magnitude greater than we would have faced if we attempted to rotate the leg about the center of mass. So if you consider the knee joint, all the mass is located distal to the knee joint, and that's going to pose a greater resistance to rotation than if we had a shorter distance of the mass distribution if we're rotating about the center of mass. Now we're going to take this through one more step here. So there are actually two ways to calculate the moment of inertia. The second method is to apply the parallel axis theorem. And so by applying the parallel axis theorem, we start from the center of mass and we'll work our way to the knee joint. So once again, nothing's changed. We still want to calculate the moment of inertia about the knee joint. We know the mass is 3.6 kilograms, the length is 0.4, the radius of gyration about the proximal is 0.528, the radius of gyration about the center of mass is 0.302. And so now when we apply the parallel axis theorem, we have a different equation. So we want the moment of inertia about the knee. We calculate the moment of inertia about the center of mass, and we have to add a term that reflects the perpendicular distance between the parallel axes here. And so in the previous formula, I used the letter D. I substituted for the letter R. It's still a distance measure. So R is that distance from the joint to the center of mass that we obtained from the table at the 0.43 with a 0.433 value. So 0.433 from the proximal end times the full length, which is 0.4 meters, will give us a center of mass distance from the knee joint of 0.173 meters. And so now we substitute our values into the equation. Okay, so we expand the moment of inertia through the center of mass to our previous formula, which was m times the radius of gyration with respect to the center of mass squared, plus mass times the perpendicular distance between the parallel axes squared. And so we had previously calculated the value about the center of mass. That was our first approach. And we had 0.0525 kilogram meters squared. And we add that to the mass, which is 3.6, times the 0.4 times 0.433. I reverse the order here. It doesn't matter. It's commutative. And we square it. We run through the math, and we find a final value for the moment of inertia about the knee, which is the identical value that we calculated on slide number 13 when we used the radius of gyration value from the table. So what the examples on slide 13 and 14 illustrate are two different approaches to computing the moment of inertia, in this case of the lower leg, about the knee joint. In one case, going directly with the radius of gyration approach. The second approach using the parallel axis theorem approach. Okay, so this ends this part of our dynamics unit.